Nuclear energy has become a usual part of our lives, and a bright atomic future lies ahead. In the Soviet Union, there were 5 nuclear power plants with such reactors, but one of them is well known to all of us, the Chernobyl power plant. There were no indications of the impending catastrophe that would affect the USSR and nuclear energy around the world on that evening. At 1 minute past midnight, at the end of the scram test, the EPS 5 button was pressed. Approximately 8 to 9 seconds later, Reactor 4 of the power plant exploded. Why did the emergency protection system lead to the reactor's explosion? This is the main question regarding the causes of the accident. Hello, this is Lily. If this video gets 100,000 likes, I will make an even more interesting video for you about the Chernobyl nuclear power plant. It will be about how in 2022 it was seized by Russian occupiers, what happened to them, how they got sick with radiation sickness, and the threat of a potential explosion at the Zaporizhzhia nuclear power plant, where the Russian occupiers are currently stationed and blackmailing the whole world. Please subscribe to the channel and like the video to help it grow. While you do that, I will tell you a story. At the time of the disaster, Ukraine was one of the 15 Soviet republics. The Chernobyl nuclear power plant is located in the north of Ukraine, near the border with Belarus. The main element of these power plants was the RBMK reactor. RBMK is a type of graphite reactor that was used since 1970. Reactor number 4 was in operation for only 2.5 years. These are the main systems of the RBMK block. The nuclear reactor produces a large amount of heat. Water, as a coolant, circulates in the loop. It passes through the channels of the reactor and partially turns into steam. The moisture separates from the liquid water and drives the turbogenerator, which produces electricity. The spent steam is condensed using water from the cooling pond and fed back into the main loop. The reactor operates at full power for several months in a row. The structures necessary to accommodate these systems were enormous. Parts of the block were located inside separate concrete buildings. The reinforced concrete shielding around the reactor was 2.5 meters thick. The reactor was located inside a steel housing. Inside the hermetic casing there was a graphite lining. The active zone of the RBMK reactor contained a large amount of graphite, necessary for the nuclear chain reaction to occur. During the decay of uranium-235 nuclei, neutrons are formed, which move at a speed close to the speed of light. These neutrons move too quickly for efficient capture by uranium nuclei. Neutrons slow down while moving through graphite, and as their speed decreases, the probability of their capture by uranium-235 nuclei increases. Graphite is called a moderator because it slows down neutrons. Each graphite block has an inner cavity for fuel channels and control and protection rod channels. Water under high pressure is pumped through these channels. Uranium fuel has the shape of cylindrical tablets. Each nuclear fuel tablet contains thermal energy equivalent to a truckload of coal. The reactor must have a kind of a switch and a means of controlling power. This is done using control and protection rods, CPR. They are made of boron carbide, which is a good neutron absorber. When all the rods are fully in the active zone, they prevent the chain reaction. The reactor operates at full power with approximately 80% of the CPRs withdrawn from the active zone. If the CPRs are completely removed from the active zone, water fills their channels. Graphite displacers were added to the bottom of the CPRs to replace the water in the channels. Replacing water with graphite reduced the parasitic neutron absorption by water and thus increased the reactor's efficiency. The explosion was a result of a design error in the control and protection rod system, known as the Yend effect. It caused a rapid and short-term increase in reactivity and therefore power, while the neutron-absorbing rods should have reduced this reactivity. The graphite displacers, located in the central part of the active zone, were fully lifted by the rods. The bottom and top 1.25 meters were filled with water. The accident process developed specifically in the lower part of the active zone. We will return to this later. The purpose of the test was to experimentally verify the possibility of using the mechanical energy of the turbine generator's coast down to supply its own needs in the event of a complete loss of power until the backup diesel generators could be started. 3 previous attempts had failed. The test was supposed to be carried out during the reactor shutdown. However, on that day, the shutdown of the block was postponed at the request of the Kyivmenergo dispatcher, and the reactor remained at half power for most of the day. This led to two of the most important factors of the disaster. First, the poisoning of the reactor with xenon. Second, the test was carried out by a less experienced night shift, which was not properly informed about the test program. At 1 a.m. on April 25, the process of reducing the power of the power unit began, but it was interrupted at 7 a.m. by the dispatcher's ban on further power reduction, leaving it at 50% level. The permission to unload the power unit was received at 11 p.m. after a 16-hour break. At 0:05, the thermal power of the reactor reached the planned 720 megawatts, or 22% of the total power. During the transition from one control system to another, the operator allowed the power to drop practically to zero. During operation at half power in the reactor's active zone, a process called xenon poisoning developed. Xenon-135 absorbs neutrons very well, and after the reactor entered this state, it was impossible to return it to nominal power for a certain period due to the decrease in the number of neutrons capable of sustaining the chain reaction. Xenon-135 has a half-life of 9 hours and accumulates at low power. The deputy chief engineer of the plant, Anatoly Dyatlov, decided to continue preparing for the test under these conditions. After the power failure, Anatoly Dyatlov allowed or demanded that the power be raised to a level of 200 megawatts instead of the 700 megawatts specified in the program. The process of raising the power somewhat resembled pressing the gas pedal in a car with the handbrake engaged. After an hour, the operators raised the power to 200 megawatts. The test began at 1:23 a.m. and lasted 40 seconds. According to the program, the reactor was supposed to be shut down by the EPS-5 button at the beginning of the test, but the button was pressed later for unknown reasons. The test of the power surge regime proceeded in a calm atmosphere. Perhaps you have seen a new switch-like design with a protective cover, but at that time, it was a button. The EPS-5 button, which was pressed by senior engineer Leonid Topchinov, had a similar appearance. At the moment of pressing EPS-5, the control and protection rods were in this configuration. There were less than 8 manual control rods in the active zone, which the staff did not know about. According to the regulations, there should have been at least 15 manual control rods in the active zone. This indicator is called the reactivity margin, or RM. But due to the state of the reactor, this indicator, RM, was very small. The EPS-5 signal causes all the rods of the automatic control system to move simultaneously into the active zone. In the lower part of the active zone, graphite displacers began to enter, replacing water with graphite in the channels. The small RM itself was not dangerous. The emergency protection due to the end effect with a small RM became a trigger. Graphite has significantly less ability to absorb neutrons compared to water. Therefore, when graphite displaced water, reactivity sharply increased in the lower part of the active zone, and consequently, power increased. Boron carbide was located higher and did not affect the reaction at the bottom. The rapid increase in power caused the formation of steam bubbles, i.e., voids, and consequently weakened the ability of water to absorb neutrons due to the reduction of its average density. The steam coefficient of reactivity in RBMK was positive, meaning the appearance of steam in the channels caused an increase in energy release. The pressure in the technological channels sharply increased due to intense steam generation. The heat-generating assemblies began to disintegrate, and then the channels themselves. This accelerated the dehydration of the active zone, increased power and pressure in the reactor vessel. The destruction of just 4 channels was enough to lift the upper protective plate, which was the first explosion. After that, the entire active zone was completely dehydrated and the reactor accelerated on prompt neutrons, leading to its complete destruction. This event is often referred to as the second explosion. The upper protective plate of the reactor, weighing 2,000 tons, was thrown upward. The explosion destroyed the ceiling and part of the walls of the central hall. The north wall of the block partially collapsed due to the explosion, revealing the steam drums and main circulation pumps. Firefighters who were fighting the fire near the block walls saw glowing pieces of graphite lying everywhere. They did not suspect that they were receiving lethal doses of ionizing radiation. This was a thermal or steam explosion. It was not a nuclear explosion in the sense that we know it from nuclear bombs. But the physical nature of the second thermal explosion was essentially nuclear. The control room shield of the 4th block was dismantled approximately 25 years later. Some equipment was reused, while the rest was stretched as souvenirs by those who had access to this room. Soviet scientists were aware of the positive void coefficient at low reactor reactivity margins. Incidents at similar reactors had occurred before. For example, in 1975, on Unit 1 of the Leningrad Nuclear Power Plant, after the EPS 5 button was pressed at a low reactivity margin, reactor channels were damaged. And at the Ignalina Nuclear Power Plant, the positive void coefficient was observed during the physical startup of the reactor. These and other accidents at RBMK reactors led to minor changes in the regulations, but the danger of some of the regimes was not mentioned anywhere. The RBMK reactors were considered completely safe. However, design flaws were concealed by the reactor's designer. If operators knew about the danger of working with a small reactivity margin and the behavior of the emergency protection system, they could have avoided this situation. Operators were confident that the Level 5 emergency protection button EPS 5 would shut down the reactor in any situation. But it turned out that under certain conditions, the emergency protection system could cause uncontrolled power increase. The IAEA Commission found that at power levels below 50%, the control instruments did not provide full feedback. The danger of working at low power and with a small reactivity margin was not well described in the operating documentation. Operators could not see some important parameters and often had to rely on their own experience and intuition. Safer reactors of other designs use water both as a coolant and as a neutron moderator. The use of water as a moderator has allowed for better control and has prevented similar accidents, as well as making the active zone much smaller. When water is converted into steam, its ability to moderate neutrons decreases and reactivity drops. Higher enriched uranium is used for these reactors. Graphite was considered the best moderator due to the ability to use cheap low-enriched uranium. The transition to water occurred when improved uranium enrichment technologies allowed for its production in sufficient quantities. Looking back, it's easy to criticize the time when the level of science and computer modeling was much lower than it is now. People can dream of the most wonderful things, but people are also responsible for everything that happens. We will never know all the details of what happened at the block control shield of power unit for that night. Most of those who were there gave their lives heroically performing their duties to prevent even more terrible consequences and save the world from a more global catastrophe. One can talk a lot about the mistakes in the design of the reactor, the lack of information among the operational staff, and the violation of the program. But this story is also about incredible bravery and self-sacrifice. Sometimes people experience failure, but much more often we are able to achieve success. Thank you for watching. Please like this video.